Okay, in this first lesson, we're starting chapter 2, and we're talking about how we worry about finding instantaneous versus average velocities. So let's suppose you're driving along a highway at a constant speed of 72 miles per hour. What would this look like if we were to graph it? So we want to graph a model that displays the distance you've traveled as a function of time. So if I'm doing that, I have my time down here on the x-axis, and my distance over here on the y-axis. And if I'm going at a constant speed, while I started at 0, my distance away from where I started as time goes on is getting further and further and further. And because it's constant, I know it's a straight line. So again, here's that graph. My time again at the bottom, my distance is on the y-axis. And the slope of this line, as I've graphed it, represents my 72 miles per hour. Remember, when you're finding slope, you take any 2 points, you find the change in rise, the change in the run. So this is my change in distance divided by my change in time. So in this case, my distance is miles, my time is hours, so that's where I get the miles per hour. So the slope in this case is representing the speed that I'm traveling at. Okay, so what happens if you're driving along, but now your cruise control is broken? You can't keep a constant speed, so your speed is varying as you go up and down this hilly interstate. What's the graph going to look like? Well, when you start, you might be going at one speed, and then you might get faster, you might get a little slower, you might get really fast, you get a little slower, and it's going to keep changing. So we don't have a constant speed. Okay, so now that we have that graph, we see there's not a constant slope. So how are we going to figure out what our average velocity is? So remember that your average velocity is the distance traveled divided by the elapsed time. So here's that same graph we drew. Again, we want to know how are we finding that average velocity. So in order to find an average velocity, you're basically just finding the average slope between any 2 points. So I can pick any 2 points, and I would find the average slope to figure out what my average speed was. Okay, so let's look at an example with actual data. So I said we're looking at a rock that is launched vertically in the air. The height of the rock h in feet is given at any time in t seconds as h of t equals negative 16 t squared plus 96 t. So my graph is showing the path of the rock from 0 to 6 seconds. So we're really only looking at this part of my graph. Right, the graph goes on and on forever, but we can't have negative time, so it goes to 0. At 6 seconds, it's back on the ground, so we're not worrying about that. So we're not going to worry about the extensions of that graph. That's all we're looking at. So if we want my average velocity of the rock from 0 to 6 seconds, I'm essentially saying if I draw a line from the 0 to 6 seconds, what is the slope of that line? So the slope of that line is my height at 6 seconds, which is 0, minus my height at 0 seconds, which is 0, all over my time, 6 seconds minus 0 seconds, my slope is 0. So if I only look at the starting and the end, my average velocity was 0 because I started and ended at 0. Now I obviously didn't travel at 0 the whole time. Okay, same problem, everything's a setup, except now I want to know just what's the average velocity on the interval from 1 to 3 seconds. So now I'm looking from here, 1 to 3. So again, to get my slope, I'm just finding slope just like you did when you first learned lines. So it's going to be 144 minus 80 divided by 3 minus 1. 144 minus 80 is 64 divided by 2. So this works out to be 32 feet per second. Which makes more sense. On the last one, when we looked at the entire interval, it didn't move, which is true. The initial and ending height were the same, so the velocity was 0. It didn't move. This time we can see it's definitely traveling at a speed. So here again, we're just showing that a little bit clearer. There's my exact line drawn, finding my change in rise, my change in run, to calculate my slope. Okay, again, same problem, except now we're looking for the average velocity on the interval from 1 to 2 seconds. So again, to find my slope, I'm taking my change in height, so 128 minus 80, divided by my change in speed, 2 minus 1. So here I have 48 divided by 1. So my average speed here is 48 feet per second. And here's that same information just being explained a little bit differently with a picture. So now the question is, as I get closer and closer to 1 second, how do I figure out what the speed is? Well, it's greater than 0, but is it greater than 48? Is it greater than 32? So we started by looking at this line. Then we looked at this line, and we're trying to figure out what's happening right at this instant. That's what we need to figure out. Now, both of these lines that we've drawn are what we call secant lines. They're lines that go through a curve but don't hit it. So to find the instantaneous velocity right at this green, I need a line that just touches the green and passes on. And this is what we call the tangent line. So to figure out what the tangent line is we're still following slope between any 2 points on that curve, but we're waiting for that change in time to get closer and closer to 0. So we're shrinking this distance so it's down to almost nothing. Now, we can't actually make the time change 0 because then we'd be dividing by 0. It doesn't work. So that doesn't quite work for us. So we've got to do a little bit of trickery. And that trickery is what's going to give me the equation of that tangent line. So again, as that interval is getting smaller and smaller, the slopes of that secant line are going to get closer and closer to what that tangent line is. So when we first looked at my interval, the 1 to 3 and the 1, 2, the lines were secant, and I just need to keep making them smaller and smaller. So as I keep making it smaller and smaller, I can kind of predict what it's going to be looking at the trend. So again, here we just have another visual. We're trying to figure out what this red line is going to be. And I'm predicting that the slope at exactly 1 is going to be 64 feet per second. And the way I figured that out is we calculated the slope between 1 and 2. We found that was going to be 48 seconds. And this time I've given us a little bit more information. I calculated the slope between 1 and 1.5. I calculated the slope between 1 and 1.1. So I'm getting much, much closer. So as the distance is shrinking up in time, I'm getting closer and closer. And so this trend, as I keep going, is getting smaller and smaller. And I could use 1.01 for my time. I could use 1.001 for the time. And eventually I'm going to see it's going to get closer and closer to that 64. So the instantaneous speed, instantaneous velocity, is equivalent to the slope of the tangent line at that exact point. So again, this slide is showing me how we figured that out. And so this is where limits start to come into place. As I'm getting closer and closer, what's happening? So as I'm coming closer and closer in, as my time is getting closer and closer to 1, and I subtract those, that distance is getting smaller and smaller, and it works out to be that 64. Okay. So again, just to practice our calculations, we can do it with any type of curve. If I want to find the average velocity of a slope, the average velocity or the slope of the secant line of an object, I have to look at that interval. So my interval is 0 to 8. So I'm getting my slope of my secant line. The secant tells me average velocity, and that's going to be the function at 8 minus the function at 0 all over my change in time, which is 8 minus 0. Okay, so I calculate my S of 8, and I end up, and I did do this ahead, I plugged it right in. This is negative 50.6 minus S of 0 is just going to be 23 divided by 8. So this ends up to be negative 9.2. And I didn't give units, so it's whatever the distance per time is. We can also find average velocity even if we're not giving specific values. We can do it with variables. Same thing happens. So the slope of my secant line to give me my average velocity, so velocity average, is going to be S of 1 plus h minus S of 0 over 1 plus h minus 0. Now, when you calculate S of 1 plus h, you plug in the 1 plus h for the t's, so you're going to have to square it. Remember to double distribute to clean that all up. So just my S of h, when I plugged all of that in, I had negative 4.9 h squared minus 39.8h plus 48.1, and then minus s of 0 is 23, all over 1 plus h. And the cleanest I can get to that is negative 4.9h squared minus 39.8h minus 25.1, all over 1 plus h. And that would be the average velocity depending on what h is. Okay, so now that we know how to find those average velocities, finding the slope of the secant line, we want to be able to figure out how we can determine what that instantaneous velocity is. How did we come up with that 64 before in that other problem? So I've given you a new position function, s of t equals negative 16t squared plus 89t plus 64. And what I did was I found the average velocities at all these given intervals. So I found the average velocity from 3 to 4, and then I got closer, right? So if I'm looking at a number line, and I want to know exactly what's happening at 4, I have to approach it from both sides. So I'm starting with 3, and I'm looking at that change, and I find that the average velocity there is negative 23. Then I got closer, and I went to 3.9. And 3.9 to 4, my average velocity was negative 37.4. And then I went to 3.99. I got negative 38.84. And then I went to negative 3.999. So I'm getting super close. I'm approaching and making that difference closer and closer to 0. And I'm seeing I'm getting negative 38.984. And then what I have to do is I have to go from the opposite direction. So then I started over here at 5. And I found my average velocity was negative 55. And then I went in and I went, okay, let's go just above 4. So I'm at 4.1 and I had negative 40.6. Then I went in a little bit closer. Negative 4.01 was negative 39.16. And then I went in even closer, and I got at 4.001, that difference, my average velocity was negative 39.016. So again, I'm going from 5, and I'm approaching the 4. So from both directions, as I get closer and closer to 4, I can see that my average velocity, my conjecture, is that my average velocity is going to be negative 39. Right? Because that's where I'm approaching from both sides. So anytime we want to find our instantaneous velocity, we're going to find the average velocities as we get closer and closer to that point, and we're going to get to there. Now, eventually we're going to be using limits to do this, but right now we're just trying to make sure we really understand the concepts behind what we're trying to accomplish. Okay, so similar question, except now I've given you the graph. So here's my slope of f of x equals x squared plus 1, this dark red color here, this guy, the parabola. And we want to find what is the slope of the graph right at this point. And then once we know what that slope is, we want to write an equation. So we have to do what we just did. We have to figure out what the slopes of the secant lines are as we get closer and closer to that point. So if I think back to, I said we were looking kind of at a number line, and we're trying to approach negative 1, and we need to approach from both directions. I could start out at negative 2 and work my way in, negative 1.1, negative 1.11, and keep getting closer and closer. I could go, negative 1.01, negative 1.001, and I can go from the other side. I could go from 0, 0.9, negative 0.9, negative 0.99, negative 0.99999. And so you want to write this and use a table. So I'm going to look at those close ones. So negative 1.1 to 1, negative 1.01 to 1, to negative 1, negative 1.001 to negative 1, and then I'm going to look from the other side. So negative 1 to negative 0.9, negative 1 to negative 0.99, and negative 1 to negative 0.999. And I'm finding the average velocities. So I have to calculate f of negative 1, f of negative 1.1, and calculate my slope. So I've done that ahead. I'm not showing that work here. And I found that from negative 1 to 1.1, my average velocity is negative 22.21. From negative 1.01 to negative 1, it's negative 2.01. From negative 1.001 to negative 1, it's negative 0.2001. Okay, so that's approaching from the left. Now I need to approach from the right. So the average slope, the secant line from -1 to -0.9 is -1.9. From -1 to -0.99 is -1.99. And from -1 to -0.999 is -1.999. So as I'm seeing this, as I approach from the left, it's getting closer and closer to -2. As I approach from the right, it's getting closer and closer to -2. So this tells me, my conjecture, is that the slope of my tangent line is going to equal -2. And from that, we want to actually write the equation of that tangent line. So remember, the equation of a line is y equals mx plus b. I know what my slope is now. It's -2, so I have y equals -2x plus b. To find b, I plug in my x and my y. So at my specific point is -1, 2. So I have 2 equals -2 times -1 plus b. So 2 equals 2 plus b. So I know b equals 0. That's my y-intercept, which tells me the equation of this line right at this point is y equals -2x. And that kind of makes sense. The slope of this line has to be negative because it's decreasing. We approximated it, and it certainly looks like it's hitting pretty close to 0 for the origin for a y-intercept of 0. Okay, so we've been focusing on speed, and speed is a little bit of a funny thing because in order to measure it, you have to have a before and an after, right? The individual is really hard. So limits are what's going to help us do that. And that's essentially what we're doing. We're looking at what's happening to the slope of that secant line as it's getting closer and closer as that distance is, or excuse me, the time is getting closer and closer to 0. So limits are what are going to help us do that. And we're going to be talking all about limits in chapter 2. So it's really important that we're understanding this concept of it before we make it a little bit more abstract. We can kind of understand what a velocity is before we just start looking at random graphs and things. If you have any questions with this video, please shoot me an email, and I will see you during class.